Welcome to this explainer on Microsoft's SchGen. We're going to dive right into how AI is literally bridging the gap between natural language and complex hardware design. If you've ever spent hours, and I mean hours, wiring up a schematic, you're definitely going to want to pay close attention to this.
So here's a question for you. Can AI really design a circuit board from a simple English prompt? I mean, historically, PCB prototyping, it's a grind, right? It's an incredibly tedious, expertise-heavy process requiring deep knowledge of embedded systems and electronics. But what if you could just tell it what you need? Let's look at how close we actually are to that reality. Quick roadmap for today's explainer. We're going to meet Microsoft SchGen, walk through its generation workflow, look at how the hardware AI is trained, evaluate its performance, and wrap up with its current limitations and next steps. Section 1. Meet Microsoft SchGen. Let's jump right into what this tech is and how it's shaking up the highly technical world of hardware design. All right, so at its core, SchGen is a large language model, but it's been supervised and fine-tuned specifically for PCB schematic generation directly from natural language requests. It's actually an open-source model. You can grab it right now on Hugging Face under an MIT license. It's built expressly for research, benchmarking, and AI-assisted hardware prototyping. Basically, you type what you want the circuit to do, and it goes to work. And the sheer scale of the foundation here, it is massive. 20 billion. That's right, 20 billion parameters. SchGen relies on the GPT-OSS-20B base model, meaning all of those parameters are dedicated entirely to this super specific task of hardware design. That is a massive amount of computational brainpower, hyper-focused precisely on generating circuits. Section 2. The schematic generation workflow. Let's move on and look at the actual translation journey. How does a simple text prompt morph into a physical circuit design? Okay, here's the real game changer. SchGen generates executable Python code, not static images. This is exactly why it matters so much to engineers. It's not just sketching a pretty picture of a circuit that you then have to manually recreate from scratch. No, it's generating editable, programmatic hardware representations that interact with custom APIs to render directly into KiCad. To make this totally practical, Microsoft lays out a really clean 4-step workflow. First, you just give it your natural language request. Second, the AI spits out the Python schematic construction code. Third, you execute that code to actually render your KiCad schematic. And fourth, this is absolutely crucial, you verify the outputs using standard ERC and DRC tools. It's a fantastic way to ground an abstract AI into a highly practical EDA pipeline. Section 3, Training the Hardware AI. So how did they pull this off? Let's lift the hood and look at the specs and data powering this code-to-schematic bridge. Looking under the hood, we've got a supervised, fine-tuned architecture boasting a context length of over 13,000 tokens. That gives it a really solid memory window for complex text inputs. But get this, the training efficiency is absolutely staggering. This 20 billion parameter model was trained on a single NVIDIA A100 GPU in just about 21 hours. Literally 21 hours. That is incredibly lean for something this capable. So how do you teach an AI hardware engineering in under a day? Well, it's all about the data. The researchers built a custom synthesis data set of about 8,000 paired natural language requests and Python code samples, and they used this really clever human-in-the-loop setup. They had GPT generate draft schematics, then actual human experts swooped in to correct and annotate those drafts. Finally, LLMs generated the user requests that perfectly matched those accurate models. That super tight, high-quality loop is exactly what gives SchGen its magic. Section 4. Evaluating a SchGen performance. All right, the model is trained. Now, how do we actually measure success in AI schematic generation? Because let's face it, generating text is one thing, but generating physics? That's a whole different beast. So they rely on 3 incredibly strict hardware evaluation metrics. First up, valid circuits. Does the generated code actually execute and produce a working schematic? Second, spatial violation. This measures overlaps between symbols, labels, and wires, because real-world physics matter. And third, netless accuracy. This checks if the connectivity actually matches a ground truth design. These metrics assure hardware engineers that success relies on real electrical and visual viability. And how did it do against those strict tests? Well, SchGen absolutely outperforms several frontier LLM baselines on schematic generation tasks. The big takeaway for you here is that if you give generalized frontier models and this hyper-specialized SchGen model the exact same custom APIs, the specialized, fine-tuned model consistently wins out. Purpose-built training matters, for sure. Section 5, limitations and next steps. Finally, let's talk guardrails because managing expectations is absolutely vital with any early-stage research system like this. While it's super impressive, we have to keep our feet on the ground. SchGen shines right now when you're working on small to medium-scale modules, hobbyist or open-source hardware designs, and using English language requests. But it definitely struggles with RF or high-frequency circuits, heavy industrial hardware, massive multi-board systems, and especially safety-critical applications. It's a brilliant tool, but yeah, no, you wouldn't use it to wire an airplane today. And because of those weak points, mandatory output verification is incredibly important. Generated schematics must always go through strict electrical rule checking, design rule checking, and comprehensive human engineering review. You can't just copy-paste the AI's output into a manufacturing pipeline without a human expert validating the whole shebang for safety and functionality. Which brings us to this perfect quote from the source material. SchGen is intended as an assistive tool rather than a fully autonomous hardware engineer. Hit the nail on the head, right? This is the core ethos to keep in mind. This AI is an intelligent Copilot. It's there to assist you, to speed up your workflow, and handle that annoying boilerplate code. But it's absolutely not a replacement for your human engineering expertise and intuition.
So I want to leave you with this provocative thought. If AI can now handle the schematic boilerplate directly from your natural language prompts, saving you hours of tedious setup, what hardware are you going to prototype first? How will you use this open-source tool to accelerate your own creative workflows? Thanks for joining me for this explainer. Keep learning, keep building, and I'll catch you next time.